I also send you an access code to Mastering Astronomy. Did you see that? A few minutes ago. So that access code will grant you access, of course, to Mastering Astronomy. And Mastering Astronomy is a platform where you use replacing the clickers to come up with questions during classroom. Why is not mirroring?
You sent it through Canvas?
Yeah. Did you receive it?
I didn't receive it.
No.
No one received it? Well, meanwhile, my iPad is trying to wake up. Come on. Let me see here. You got it?
It's under announcements.
Yes. Yeah. Okay, you went through the announcements. Yeah, there you go. But it's here. So you have to punch all these letters, and then you're gonna find the course, and then make sure you have your name there. Don't put any funny name, like your code name. I mean, some students, some of us put code names in email, but I need to identify you because that's how I'm gonna grade. And you don't need to put your student ID. I don't need that one. Okay, very good. Now, what is happening here? Why is it not populating? Well, for some reason, I'm not able to pull up my iPad. I wonder why. Um, so I will just run. Why is that? Why all this happen on Monday? See, it's coming back, enable, and you're good. Come on, man. Screen mirroring and doesn't go. I have my remotes, and it doesn't go. Okay, well, we can do it, we don't do it. Anyway, so yeah, I can stop and go backwards. Let me put some lights back here. Okay, chapter 4 is maybe what I would consider the most challenging for students in the Astro 10 and Astro 10L sections. And the reason to that is explains how we make astronomy scientific in the sense that what we say and do and expose and treat is based on evidence. Think about in science, if you ask any kid to describe a scientist, this is changing, but that experiment was done. So young kids, they perceive a scientist as a male person with a beard and a white kind of a garment, doing annotations on a board. That's the perception, which is changing because, in fact, the growing number of female entering PhD programs in STEM, in science, is by far surpassing male. Although the absolute numbers of males are still kind of a little bit above, but it's going to reach an equilibrium, and that's what we want. But the perception is still there. Maybe it's going to change because of cultural changes in our society. But another perception is astronomers know about the universe because they see it. You also ask kids to draw the picture of an astronomer. Again, the male that is looking through a telescope. So it's easy to associate the telescope with astronomy because it's an instrument we use to observe sky objects. But we don't see the sky objects to build knowledge in astronomy. It's a completely different story. So astronomy in the 1800s was done like that. Galileo Galilei did that, and we learned that. Galileo Galilei looked at Venus, saw Venus in Gibbous phase. We have that in HCM. So Venus in Gibbous phase, and then was able to prove that there was something else that wouldn't go around Earth alone, was going around the sun. And then he saw the moons of Jupiter, which allow him to indicate that 4 objects were not going around Earth alone, going around Jupiter. And the geocentric worldview started crumbling right there because of observations, visualization of things. But sky objects other than Jupiter, Saturn, Uranus, and Mars, which are relatively close, you can't distinguish, you can't see anything just by visualization. In the 1800s, astronomers were sort of an artist because there was no means to impress and register what they could see as extended clouds. So the first attempt to describe a galaxy to other people besides astronomers was you observe the galaxy at night. Now think about it. Everything has to be dark, right? That's what we do. So you are in the dark, and then you look through powerful telescopes built in the 1800s, right, with big lenses. And then you could see some structure in the galaxy. Now you see that, memorize, and then go to a drawing paper, and then you do the marks. I don't think they would turn on, lights or candles because would make their eyes too much sensitive to light. So when they go back to the observation, they couldn't see well. So I would imagine they would have some technique, some shield, some red light. I don't know. But that's how they did. They would observe and then draw, and then compare the draw with observations and do it again and then improve. And then you see these pictures being released of fantastic objects. This is 1800. So 1900 you had photographic plates. Now we have CCD, same technology you have in your cell phone to store images. So astronomy nowadays is done and is scientific because we understand light. So if I have to summarize what is the important aspect of light in astronomy, light is something that has the property of interact with matter. And when interact with the matter, not dark matter, but matter, which consists of protons, neutrons, electrons, and a combination of creates, structures like your body, like my body, like this environment, like planets, stars, gas, galactic halo. So matter, when interacts with light getting printed with some information. And then light just keep on traveling, right, through space. And let's say a star very far away produce some energy we call light. That light travels from that star passing through interstellar material. And as it does, it gets information of what is in there. And then it passes, let's say, through our atmosphere, and then it gets information of what is in our atmosphere. And then it goes through the telescope, and then astronomers take that information and then encrypt it in CCDs or in cameras like the one you have in your cell phone, but much more equipped and developed. And then now you can look at it and then understand what's going on out there without going. And that was one of the major advancements in astronomers in the early 1900s, when a technique that is called spectroscopy was invented. So what spectroscopy does is to take the light and spread the light into its basic constituents as far as frequency is concerned, as far as wavelength is concerned. And by the way, we are going to see that. And by spreading out, you can find details of what light exactly is. And those details enable astronomers to say, hey, that star is moving away from us. That star is rotating faster. That star has 30% or more of helium for some crazy reason, or that star has certain metal abundance that I can measure right here, and all of that. That star is exploding right now, or that particular star is full of activity and has spots, has all of that. And then you have these nice pictures produced, or not pictures, but cartoon produced by artists, which try to reproduce what astronomers tell them about their findings without being real pictures. You know what I mean? So that is what light is so important, and I would say is a fundamental chapter. And so keep track of spectroscopy. Is a fundamental technique that astronomers use to understand celestial objects. So also in this chapter, you're going to see something named photons. So light has a funny property. Light can behave like wave. And I mean, my friend student over there went to Santa Cruz, so saw a lot of wave, which is energy propagating through water. And when you set energy in the water, so you see wave-like movement coming out of the point you touch the water. So if you throw a rock on the water, so out of that point the rock hits the water, you're going to see wavelength comes out. So it's energy pretty much propagating. You might have seen simulation of earthquakes. It's another type of wave, seismic waves. So when two major blocks move past one another, it generates energy. So that energy just moved, through the ground, upward, downward, and there are different types of seismic waves. Three, in fact, we are studying, we will study, and then when you receive that energy, you see the shaking going on, earthquakes. So it's sort of a transverse waves or push-pull type of waves. We'll see them. So light behaves like a type of transverse wave. You see that. But also light can behave like particle. So which is kind of a weird. Wave is something like this. A particle is something like this. This duality is one of the most striking aspects of nature when you go to its fundamental properties. I mean, just think about it. You are what you are. I mean, you looks different sometimes because you have a better mood, or you wake up better, or you have different clothing. But you are what you are. In the case of light, it was found that light could behave like this thing over here if you use certain instruments. Like if you use, I'm not going to go in a lot of detail. I might bring a bunch of little gadgets next week just to show that. But depending on the instrument you use, light can behave like wave. But if you have a different instrument, a different detector, like the one you have in the cell phone, wave doesn't work well to explain the interaction of reality light with your cell phone, but little particles, named photon, can do the trick, can explain the interaction. And then you say, okay, is light wave or a particle? And then it comes to one of the crucial philosophical aspects of science nowadays, especially physics. So exactly what reality is. So because basically we are trying to define what reality is. The reality light is what? Is this or that? And then comes to the fundamental philosophical question, and that is, well, what reality is depends on which instruments of measurement you have. Which is crazy. Einstein, just to give an idea, Einstein thought this was BS, right? Einstein was not only a heck of a scientist, but he was also sort of a philosopher of science. And then he believed, and I'm using the word believe in a very religious way. So he believed that nature was a reality, was something real. And the pathway of physics was to explain what that was and provide its characteristics. Like particles have mass, numbers, charge, and certain quantities that you can identify some object uniquely. And you couldn't determine where they were precisely. And then when, when this duality were found, and now we are saying, well, reality depends on what you use to measure, depends on what you perceive of it. Then all this idea of what is real kind of crumble down, and it is more dependent on what you use to explain or to measure reality. In all of this discussion, and I would stop this kind of a philosophical digression right now. It's one thing is true: nature has the last word on it. So we are trying to understand what nature is and how nature operates and how nature functions. And in order to describe nature, we have to see it and measure it. And how do we measure? Not with eyes or touch or smell or with our five senses, but with technology. And technology is what is used to describe what reality basically is. So let's go through the basics of this chapter. How come it's not going? Okay. So, yeah, most knowledge of the universe beyond Earth comes from light. We want to understand the properties of light and how telescopes used to collect light. So that's the basic things. Now, light, and that is one key aspect. Take notes, because that might be important on your cheat sheet for midterm number 3, by the way. So light has a finite speed. So nothing in nature can go beyond the speed of light, and that has been measured. So several attempts have been made to determine if something can go faster than light, and it doesn't, they fail. And relativity is built on that notion that light cannot be beat by anything else. So particles like protons, electrons, neons, muons, they cannot go faster than the speed of light. Later on in our course, we're going to learn about expansion of space. An expansion of space can lead to measurements that are larger than the speed of light. But space can have that property. Particles cannot. This slide is showing an experiment done in the 1800s, and Romer was the astronomers who made. Romer was observing the moons of Jupiter. So now we have Galileo Galilei, the telescope. This is past 1600. And the experiment is very cool to show there is a finite speed of light. And that couldn't be measured, by the way. So if Earth is here in its orbit around the sun, if Earth is here, and then you look at Io, let's say, Io enter behind in its orbit around the Jupiter. It's kind of a Jupiter occult Io, and as Io comes out, it's gonna be visible again on a certain amount of time. I don't know. So some fractions of a day, because Io is very close. So you measure that. So you're here, and then you measure when Io disappeared because it's behind Jupiter, and then you measure when Io comes back. So you have that numbers, and it's not five days, but let's just come up with a number so that you can think of. Okay, so 5 days is when it takes Io to go from here to there. Okay, I got it. So imagine now that you are here, because Earth is going around the sun, right? So when Earth is here, again, you are looking at Jupiter, and then you see Io being occult by Jupiter. And then you say, okay, I'm expecting 5 hours Io to come up there. Let's see what happened. When Io is coming out, light travels 5 hours, plus it needs to travel this much distance to arrive to your detector. It's a little bit more than 5 hours. So during measuring this delay, in fact, not this delay, in fact, yes, the delay. So it takes some more time for the light, for Io to come back behind Jupiter. Astronomers were able, for the first time, to measure, to give a number for the average distance between Earth and the Sun. So this is 2 astronomical units. So you have that time, and then you can pretty much take the speed of light, in a very precise way. And there were several other measurements that can be used to prove that light has a finite speed. No matter how intensive, what sort of a frequency of the light we are observing, the blue light, gamma rays, X-rays, infrared, they all move with the same speed, which is the speed of light in the vacuum, and nothing can beat that speed. So this picture here suggests that if you have some vibration, in fact, electromagnetic waves, or this phenomena that we call light functioning as wave, can be produced once charged particles, and I'm not going to go in a lot of detail here, but if you have electrons or protons, they have charge. Electrons negative charge, protons positive charge. If they vibrate, if they have any, as we say in physics, acceleration, change in velocity over time, this electromagnetic radiation is produced, is emitted. And then you can use this property to send signals. So if you can control the acceleration of electrons, and that can be done quite easily if you study electronics and all of that, then you can send signals through space, and these signals can be detected in antennas, and then you can read out information over long distance. So let's take light as a wave-like phenomena. So as a wave-like phenomena, the first quantity that I would like to bring your attention to is the so-called wavelength. So what wavelength is? So wavelength is the distance between characteristics of wave that share common properties. In the case here, simply shown, is the distance between the crest of the wave, or also the distance between the trough points of an wave. So that is a so-called wavelength. So wavelength, in terms of light, it's not very big. It's not kind of inches or meters or miles. In fact, it's very small. It's 10 to minus 8 of a meter, just to give an idea. So it's a very small, quantity. You can't easily measure that. You can if you have, slits, and in the lab we play with that. So wavelength is something related to distance. This Greek letter is named lambda. 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 That's how we say it. So lambda is the wavelength of wave, and sometimes you might bump into graphics that indicate light as a function of its wavelength, because wavelength is a property that is not the same throughout the whole range that light can support, light can show itself. So another quantity here is frequency. The frequency of a wave. So what exactly that is? So going to the example of Santa Cruz again. So let's say if you are in the shore of Santa Cruz and there is energy propagating through the water, and then you stay there close to the shoreline, and then you see waves coming. So if you have some way of measuring the distance between the crest of these waves, you're a surfer, right? Good, maybe. Then you have the wavelength. But what is frequency? Frequency is, in a simple example like that, you are on the shoreline, and then there comes a wave, and then it splash on your foot. And then you count 1, Mississippi 2, Mississippi 3, and you count 10 seconds, and then comes another wave. And then another 10 seconds and another wave. So let's say you have 4 of these events in a minute, 60 seconds. So then you have 4 events per minute. That is your frequency. So the frequency is the number of oscillations, the number of events per second, basically. So if you take 4, right, 4 events, 4 splashes, in 1 minute, 60 seconds, so you have 4 divided by 60, and that is the unit of frequency. It's kind of a hertz. So for my example, 4 events, called events, or gravity. This is gravity. Over 60 seconds. So you have 1 over 15, right? Kind of a simplifying here. 4 by 60, 1 over 15, 1 over second. Second. This is second. Now 1 over 15 is a number. I'm not going to calculate now. And 1 over second has a name. It's a unity. Hertz. Hertz. And it's kind of a given in H. Hertz. That's the frequency, the unit of frequency. So again, frequency is the number of events or oscillation, if you have some oscillation going on, over time. So if we are talking about high frequency, What does it mean, my example? Well, a high frequency is you are there, and then you have a splash, not just 4, but you have 10 splashes per minute. So now you have more energy coming in. So if it's you are not you, but you are a cliff, and this cliff is receiving this pounding, this shock waves with high frequency, so chances are energy will be more efficiently used to carve and destroy this cliff. That's what nature does, reshaping the landscape and changing all the time. So if the frequency is less, which means you have just one splash in a minute, then you don't have a lot of energy built up in this wave. So think about high frequency is associated with a lot of events. So you have an energetic type of phenomena. And low frequency is associated with less energetic type of phenomena. Does that make sense? It's kind of not so, I mean, I don't want you to memorize these things. I want you to kind of have a sense of what I'm talking about. You know what energy is, right? So who can tell me what energy is? What is energy? Because I'm using energy in the sense of physics here. What is energy? Give some good definition of energy. What comes to your mind? Energy. Food. It is good energy. It's called calories. Calories. And one of the things we learn in thermodynamics, you want the amount of calorie that you eat in a day go back to be the same amount of energy that you spend in that day. What happens if your intake of energy is bigger than the amount of energy you spend during your day? What's going to happen with you?
There's a lot of energy.
You gain weight because calories will be transformed in fat so that you can live through the winter. It's in olden days, right? We need a lot of fat for the winter, but not nowadays. Winter comes and we go to the restaurants and Starbucks and eat more and drink more because it's cold, and so you have to be careful there. So energy is something in physics that do things. We use the word work, right? Systems that have a lot of energy do a lot of work. And work is not just work hard, as we say it, but work is the ability of doing things, performing things, and have power to do those things. Okay, so we saw wavelength, we saw frequency, and here we have something, and I can't mark for some reason. Let me see if I can try now. Still doesn't go. So another thing is what we are calling velocity. Velocity of a wave, the velocity in which a wave propagates. What does it mean? The velocity in which a wave propagates has to do with, think about it if you are a surfer and you are sitting on a board, and then there comes a wave that is good, but it's not as good as the one that comes after, right? So what you do, you stay there. So the wave that is not so good pass by is going to take you up, and you make a little round, and then you're back to the same point. And that comes another wave, right? So if you can measure the time that it takes one crest to pass and the other one to pass too, if you time that, in other words, if you time the interval in which this wave passes through your locale to your point, then you can think about the velocity of a wave, is how much this wave propagates through space, right? So if you are a surfer, now you take the wave and then you have a process of a constant falling, constant fall. You basically what you do, you put your board right here. That's your. You put your board right here, and then you start falling, right? But when you fall, when you slide down the wave moves forward. And then it's a process by which you are falling, but you are being taken away. When you combine these two effects, you just move forward along with the wave, which is pretty cool, right? It's pretty cool. So it's kind of a falling, but moving forward because energy take you away, and then you can get your speed. So that's you have the velocity in which this wave propagates. So how do you relate those quantities? So the speed, and that is given right here, the speed divided by the frequency gives the wavelength. Or in other words, if you take the wavelength and you divide by the time it takes, these events to pass, to come in again and be repeated, that gives the speed of the wave. So in our course, I don't see a lot of situations that you are going to be measuring speed. But in fact, in physics, we change because the speed of light, although we say, okay, it can't be bigger than 300,000 kilometers per second in the vacuum. When light goes through transparent media, the speed diminishes slightly. And when it does, the wavelength changes too, but not the frequency. It's a complicated thing, and I prefer to not to bother you with the term speed here. So just keep a sense of what wavelength and frequency are, and that the speed of light is something constant over in space, and nothing can be bigger and faster, can travel faster than the speed of light. By the way, I uploaded this PowerPoint on Canvas, and you can go there, take a look, and play around with the questions. If you don't understand them, just ask me again. I will have the chance of using some class enhancement technology probably next week. Please sign up for Mastering Astronomy. So if you get late, you should have received an announcement with the new access code.
Actually, I tried the access code, it didn't work.
The access code I sent today?
Yeah.
What does it say?
Yeah, I copied it exactly from here.
Yeah, and then
Nope, didn't work.
that I didn't work. Check with your instructor. Okay, can you screenshot this because the lady wants to know if it's working.
Yeah, I have
The publisher, she just sent me. She sent me this code and I sent it to you. So just send me the screenshot of that. That would be helpful. Okay, so now if you take light, let's say the light in this light bulb, the light that comes from the sun, and then you take the light and you pass that light through some technology. Or here nature does not have a technology, but has droplets of water in suspension in the atmosphere. Some cool thing happens when light goes through those droplets. It creates a rainbow. So a rainbow is what? Well, white light, Isaac Newton, the same guy who invented the the universal gravity law that we studied last week. Newton also was very much interested in light. And in fact, Newton had his interest because of his religious belief, an association of light with something that has to do with God or perfection or something like that. And Newton had some parallel life, I can tell you. He experimented with mercury, for instance, in alchemy. If you were curious for that, I mean, alchemy was kind of a mother of chemistry, modern chemistry, but it was a weird kind of a beliefs in alchemy, like certain metals could be purified and transformed in gold. Like you could take, lead is not a good metal, but some metals were good, and you could do some transformations that would lead to gold. And then nowadays people say, nah, they didn't want to try to find gold. They were trying to find something that would transform the human being, something superhuman and super perfect. I don't know if that is true. But the point is, Sir Isaac Newton was experimenting with mercury, which you know is poisonous. We are even trying to get rid of mercury in chemistry laboratory because if it breaks, if you think I'm a little bit crazy, when I was a kid, thermometer would break in the house. I would be the one collecting the droplets of mercury to play with because it's very cool. I don't know if you've seen that. Have you seen mercury? Have you seen Quicksilver? No. It makes like it has the same behavior when you take a metal plate that is very smoothly. It's very smooth and also very hot, and then you throw a droplet of water, just a little droplet, and makes a bubble, perfect one, that moves almost without friction. I keep just going quickly like that, and then eventually it breaks down and vaporizes quickly. So mercury has the same behavior, except it doesn't break down. And if you have little droplets nearby, and if you move around, that thing, mesh. And I, kid, without having a lot of a brain, I would smash that thing and do all kind of games. Probably I wouldn't wash my hand either. Probably I have some mercury in my brain, I don't know. Who knows? But Newton had it. In fact, they exhumated his body and took his hair, and there was trace of mercury there, a lot. The guy did a lot of crazy things, right? Not just me. But why am I talking about this? Oh, because Newton, what he did, he proved that light, the white light, was in fact a combination. White does not exist as a color, as black doesn't exist as color. Those frequencies, you could call them color, real ones. But black and white, black is absence of white, and white is a combination of frequencies, different frequencies. How Newton proved that? Well, two ways. One, by passing light, white light, through a piece of glass, and then showing that this white light would diffract itself into a rainbow. And then you can put that back. So you take another prism, and then you collect this rainbow, and as a result, you have a white light coming out of it. And I hope to bring some gadgets next week and then show you that. But here, nature is doing the trick. It's taking droplets of water and creates rainbow. When can you see a rainbow in the sky? Well, it has to have some sort of a mist or raining going on, and the sun has to be on your back. So the sun is on your back, and then you are seeing this beautiful rainbow over there. The sunlight go to the droplets, and then go into the droplet and reflect back to you like a mirror, and then you see it, these different colorations, because different frequencies will reflect at different angles. So what is being shown here is that red has the longest wavelength. So if you think about light itself, and keep yourself thinking about spectroscopy, because the reach of spectroscopy is going to come up in a second. So a red type of light has a long wavelength, right? This is red. And then blue has a shorter wavelength. But you can see the blue has higher frequency. So you have more of these events in the same length studied than red wavelength. So the blue wavelength carries more energy, excuse me, than it does the red wavelength. Am I going back? Okay. And there you go. Let's use something that we Americans like to talk about it, money talk. So we have a flashlight that is sending out red. Now I'm using light not as wave, but as particles, red photons. And I have another flashlight that is sending out blue photons. And again, I'm keeping, the wavelength, the idea of a wave out of the situation here. So think about, you have some budget, certain amount of money, and let's say you have, what do you have here? Quarters, and what is this, pennies? So let's say you want $20, right? So how many quarters, how many pennies are there in $20? How many quarters are there in $20? So if you convert that to numbers, so the amount of quarters in $20 is much less than the amount of pennies in $20, right? Can you kind of get that idea? But it's the same amount of energy. So if the energy of both of them are the same, you have to collect much more red photons in order to match the amount of energy that you are getting out of a blue photon. Now let me give you a jump into the future without using time machines. We're going to be studying stars. So if you go to the observatory, by the way, this Friday we have public viewing, stargazing, and extra credit opportunities. I will send a handout today or tomorrow because you have to do something out there. If you can't go for some reason, you have to let me know if you still want to participate because I have to come up with something for you to do. But basically, if you go to the observatory, there are groups of stars, like for instance, who is there now? Betelgeuse is there. So you look at a Betelgeuse with a telescope, and Betelgeuse has some kind of an orange coloration. You say, wow, that's weird. And then you take the telescope, right, and then move down at Sirius. And then you look through the telescope, Sirius will appear kind of electric blue. And then just by visual inspection, you come to the realization that stars have a global coloration that are different from one another. Now you take your time to be an astronomy student and 1 or 2 years of undergraduate plus 2 or 3 years of graduate studies, you're going to be able to translate colors into surface temperature. So you get the property of a star just by using some instruments that will enable you to convert these colors into some number associated with temperature. So in other words, Betelgeuse is an orange type of star, is a red supergiant, which means the surface temperature is 4,000 kelvins, and Kelvin is a unit we are going to study. And Sirius is 10,000 Kelvin, so it's hotter, if you will. Which means Sirius, a square inch of Sirius surface sends out more energy than a square inch of Betelgeuse surface. Does that make sense? So if you take the same area, emitting area, both in Betelgeuse and Sirius, Sirius is by far more energetic. Now, if for some reason, and I'm not saying this is the case, but if for some reason these two stars, Sirius and Betelgeuse, we with the detector here detect the same amount of energy from these stars, it means what? It means that Betelgeuse is all inflated. It's a big star. Does that make sense? Kind of. Right? Because see, Sirius is smaller, but every square inch efficiently sends out more energy than a square inch of Betelgeuse. So to compensate, Betelgeuse just expands. So I want you to start thinking about energy, sizes, and other issues. But for now, for this chapter, what we are discussing here, without going too much, jumping here and there, is that blue photons or blue wavelengths are more energetic than red wavelengths. Now, this is a cool thing and key thing, and it wouldn't surprise me if it is in your homework, right? And it wouldn't surprise me if you see something like that in your exam and you have to ask questions. So let's try to make a sense of this diagram. This diagram is showing the entire optical range. So down here from 350, and then you have a unit here, nm, which means a nanometer. Nano is 10 to minus 9 meters. So 350 nanometers, which is a part of the electromagnetic radiation. We can see it, but it's pretty much in the ultraviolet. Right? It's not good for our eyes, by the way. So when you go outside in a very sunny day, you use sunglasses, and some of your sunglasses are said UV protection, which means it has some filter there that stripes and takes out some of this UV radiation because it damages your retina. So you don't want to, be affected by that. And then comes the part of the electromagnetic radiation we see as well. And then we see it quite well here, by the way. This is where we see the most. And then it starts to fall down to the red, and then it goes to this range here that everything to the right we call infrared. And everything here left of this range we call far or hot or hard ultraviolet. So that is your ultraviolet. So that's the visible we can see. That's the ultraviolet that we don't see it. And then you have X-rays and gamma rays. So gamma rays and X-rays, Earth do not produce them except for some atoms that here and there decay and produce some type of radiation. So, but there are stars like the sun produce X-rays. Not a lot, but it does produce X-rays. Gamma rays, you have to go to the core of stars to see it or to measure, or you have to go and witness stars colliding and exploding to determine the outflow, this burst of gamma rays. Or like we saw in simulations last week, or have neutron stars merging and exploding and producing abundant energy, most of it gamma rays that can be detected if you have space technology for that. So what we call electromagnetic radiation is these energetic things that starts in gamma rays, X-rays, ultraviolet, and look at this. This is the small window, a very small window. We humans developed detectors, natural detectors, our beautiful eyes to interact with. How do we see things? I mean, we see things because we have detectors, sensors. And these sensors collect these photons, these particles of light, and through the optic nerve, send that to the brain, and then the brain kind of makes sense of what is out there. Since we have two detectors, we can also have a sense of depth. And if we are hunters, and we sort of are hunters, we can use that to, hunt more efficiently. And that comes the infrared. We don't see it. Some animals do. I mean, heat is associated with infrared radiation. Some animals sense that, and they use that for hunting. And then you have microwave. Microwave we have in the kitchen, but microwave is a type of electromagnetic radiation. The microwave we have in the kitchen is able to produce. Why is that? Well, microwave has the property of being easily absorbed by water. In fact, heat, again, is associated with this part of the electromagnetic radiation. And vapor in the atmosphere, as well as carbon dioxide and nitrous oxide, these gases are able to retain it. Methane, for instance. So infrared radiation that Earth is eliminating as a result of processes that goes on the floor or reflecting or heat that is producing rocks when the sunlight hits in there. So this radiation try to escape, but the gas in the atmosphere retain it. And vapor is one of them. That's why we are talking about global warming, global warming gases. We'll go there later. But basically, the microwave in the kitchen produce this radiation, these little wavelengths of light, right? We don't see it. And when it passes through the water that is in your food, it warms up the water because the water absorbs that energy, right? And then from within, the food is warm up. So that's why sometimes when you put something in there, if there is more water in a place, it's going to warm up faster than in others. And say, what the hell? Why is this happening? Well, because it's not uniform. It's pretty much looking for water. So if you put dry rice there, it's not going to cook. Right? You put water. So, and then you have the wavelengths called, generally speaking, radio waves, which are the longest possible wavelength. But what is the property here? The wavelength is the shortest here, but the frequency is the highest. The energy is the highest. That's how I want you to read this table, this diagram. So if you go to the left-hand side, you have the shortest wavelength, and you have the highest possible frequency. And when you go here, you have the longest possible wavelength, and you have the shortest possible frequency, the least possible energy the light itself is carrying, right? Less energy, bigger wavelength, less frequency. High frequency, very energetic, but short wavelength. We got all of that? All good? Now, that comes the cool thing. I like to do these jumps in philosophy because, life is philosophy, basically. This part over here? This is what we developed as sensors to be able to survive. And I'm talking about, since 3.5 billion years ago, since life have been developed in this planet. So as a species, probably 6 million years. But our eyes came as a response to this range here. Now, later on, using spectroscopy, we are going to, in fact, I can bring here in the classroom and we can do a little testing. The sun produces a distribution of energy. So it has the ultraviolet radiation, has the infrared, and has a peak that is exactly here. And in fact, exactly here. That's where the sun is peaking the most. Which means if you think about the number of photons, number of particles sending out, the sun is sending out a bunch here. Not a lot here, not a lot there, but a bunch here. and then life that created us developed these sensors so that we could move around in an environment that is being bathed by this type of light, this type of radiation. Now, if we had decided a long time ago to live in caves because it was more protected, instead of going out and fight for the environment and try to get things and expand it, probably our senses would develop in a different way. Put in a different story. If the sun were not the sun, but it were something like Betelgeuse, the peak of its radiation would be here. Our detectors would be different. It wouldn't be the way it is. What I'm trying to tell you is, if you think life is out there everywhere, as astronomers nowadays, they think that's the case because life is started here very quickly and easily. Earth was formed 4.5 billion years, and 500 million years later, 4 billion years ago, life was already springing in this hot planet at the very beginning. So we don't know how it started, but seems to be something simple, so much that there is this feverish way on to find life out there. And I know this class is going to be over when you are pretty much receiving news from James Webb Space Telescope. And one of its main missions, it's going to be launched next year, is to find fingerprints of life in other star systems and other planets. And so you guys are going to, before you close your eyes forever and don't see this type of radiation anymore, before this happens, I swear you're going to hear about life in other places besides Earth. Why am I saying that? Because life responds to whatever source exists. So life that lives in Mariana Trenches, which is the deepest part of Earth in ocean water, there is no sunlight there. So you don't see life there with eyes like ours because they don't work. They don't do things. So life develops different types of senses and search for different types of food besides sneaker bar, right? So they go in volcanic type of chemistry to find its way to survive. Life always prevails. Now let's go to, 5 minutes to go, spectroscopy. What a spectrometer is? Now we are talking about spectrometer. What do they do? So a spectrometer has the ability of taking a picture of this. So let's say you take the light and then it spreads light in a rainbow this size. Red and blue and red. This is a type of spectrometer. If you have more money, you can buy a spectrometer that will take the light, the same white light, and spread like this, blue and red, increasing the power of spreading out, allowing you to see fine details in between these frequencies. And when this is done, let me see if I have a picture here. I don't know if it's done. Oh, it doesn't. And when it does, what we find is this is going to be, in fact, extensively explored in later chapters, chapter 10. So let's say you have a rainbow like the sun. This is the blue. And then the sun goes like this, and then it falls down. This is the red part, or infrared, in fact. Infrared. This is the optical with the bluish here and the red there. So if you have a spectrometer, you can see all of that. you can see a not so much intense blue, a very intense optical, and not so much intense infrared. Okay. But let's say you take a little piece of it here, and you build a spectrometer that has what we call high resolution. It can resolve with detail. When this is done, this insect here, so this little region, which I am going to show in red right here, this little region here, we can expand. Except when you improve the resolution of a spectrometer, what you find is a bunch of little details. And these details we call lines. Lines. Those are absorption lines. Here is an emission line, absorption, absorption. And there comes the question. Where that energy goes? There is some missing energy here. You know where did it go? To the gas that exists in that atmosphere. The gas in there absorbs these photons at very selective frequency because that's how atoms behave. So basically, by analyzing these lines, astronomers can identify the chemistry of stars, the chemistry of galaxies, if quasars are moving away or towards us, if all, in fact, they are all moving away from us, and all kind of a cool information that exists out there in the universe. We can use Doppler effect. You might have heard that before. Doppler effect is a technique that uses the displacement of these lines to give us speeding tickets. Who got a speeding ticket before? Twice. We all did. I mean, unless you are very careful or you haven't driven yet. So you see this guy is kind of hidden somewhere with something pointing at the car. What are they pointing? They call a lidar. So it sends a little infrared pulse towards your car that bounces back, and when it comes, these certain frequencies in there are displaced, and that can be pinned down to the speed of your car. There's no debate there to be done. So the technique can be employed here, can be employed to identify what is out there in the sky. It can measure the speed of stars as well as it can measure the speed of your car down here. Okay? So Wednesday, if you're not here in the beginning of the class, we have midterm 2. It's going to be chapter 2 and chapter 3. Go to L232 as midterm number 1. Bring 1 page of notes, and chapter 2 and 3, this is not part of midterm number 2.